All right, I'm going to show you a couple things here. This is, okay, so what we're doing here, this kind of put this in context. It's been a weekend. This is number 9. So we are trying to, we're calculating derivatives old school. We're using limits, right? We're not doing these using our fancy tricks yet. That's coming up this week. So we're still rolling old school with our limits, but I want to show you a little trick here on some of these. Okay, hold this thought for just a second, because we're going to come back to this one. Come right back to this one. Never mind. Okay, so I want. So without looking at your notes, let's see if you can write down in your notes the definition of a derivative, the limit definition of a derivative. Right? But don't just only look where you're writing. Don't be cheating. See if you can remember it. See if you can remember it. I'm going to write it up here, but don't look up until you're done.
Wait, the equation or just?
Yeah, I want to. You finish this up. I'm going to start you off here. F prime of x, which means our derivative, right, is equal to the limit of etc. Okay. See if you can write it down. So don't look up until you can check yourself when you're done. But I want to see if you can challenge yourself to do that.
Oh my gosh, I'm so sorry. I remember reading this a moment ago.
What if you put, is it okay to put H instead of delta?
Yeah, that's fine. H is fine. Yep, you bet.
Thank you.
Okay, do we get it?
No. Yes.
Okay, so now the important thing here is what I really want you to be able to do is attach that definition to the picture that we draw all the time, right? So here's our picture. Remember what this is, this whole trick that we're doing, this tangent line problem that we solved with calculus was a very clever trick. We took a slope of a secant line and used a limit to convert the secant line into a tangent line, right? And so here's the secant line that we had, right? We've got these 2 points that we're using for our secant line. What are the coordinates of those? First one is x, f of x, right? So we get the x value and the y value. And then the other one was, okay, and good. Okay, and then so all we had to do was make a slope triangle out of this, and the slope triangle gives us our difference quotient. And that's what we're taking the limit of to turn it into a tangent line, right? So really we just did this, right? All we said was that. So rise over run. The rise we said was, we might call it delta y, but change in y, so it's going to be this y value minus that y value, right?
Delta x.
So f of x plus delta x, that y value, and there it is, right there, minus f of x. And so that difference, we could call delta y, which is our rise over our run, right?
You kind of lost me for a second.
Okay, let me slow down. Question, ask a question.
What was the side part again?
All I'm doing is I'm just showing you that if this, here's the y value of our second point. Here, right? So if we just draw a horizontal line across there.
Oh, okay.
There it is, right? There's the y value of our first point. And so the difference in those is the rise, isn't it?
Yeah.
That's delta y. Well, there it is, right there, right? There's delta y. The bottom is just delta x. x plus delta x minus x is just delta x, right?
Okay.
So that's how we get our difference quotient, right? Okay. There's another way to do this though. There's an alternate form of the difference quotient, which is not a huge, anything you can do with one, you can honestly do with the other. But in some cases, it makes the algebra maybe just look a little bit simpler. And it's a good thing to see anyway, because it's just another way of doing the tangent line trick, of taking a slope of a secant line and defining a difference quotient, and then taking the limit so it becomes a tangent line instead. Okay, so look what else we could do with this. We could take this picture and redraw it. Function will stay the same, but we're gonna redraw. We're gonna use a new scheme to label our 2 points. That's all we're doing. So there's F. Let's make this, let's call this C. Make sure I do this exactly like the book. I actually don't really like the way the book does this, but it's fine. I just want to make sure I do it just like the book so you can look back at it. Okay, so they do, oh, that's kind of weird. So they do, okay, they put the X there, which is fine, I guess. Seems to work. And we'll call this one C. So what are the coordinates at that point right there? X, f of x, okay. So this is at C. What are the coordinates going to be there?
C.
C.
Yeah,
C and MC.
F of C, good.
Oh.
Okay, so if we draw our secant line again then, okay, how do we define the difference quotient now? What is, based on this picture right here, what is delta y going to be?
F of C minus F of X.
Good.
Wait, why is it different from the other one?
Well, because we, instead of calling it x and x plus delta x, we just called it x and c. Okay? What's delta x going to be in this case?
X minus C. C
X
minus
plus
X.
C?
C minus x. Okay? This, man, they do this so backwards. It should be x minus c.
Yeah, I was gonna say, that's what I wrote down.
Okay, I'm going to flip this around. Their drawing is kind of messed up. It really is. It's kind of messed up. So let's ignore their drawing and we're just going to draw it this way. Because this will make more sense to you, I promise. Let's label these points instead. We really want to call this one C and this one X. And this will match what we did better. Because last time, remember what we did in our previous picture, this was X and this was X plus delta X, and we took the limit as delta X shrank to 0. So sort of visually what we did is we took this right point and we drew it back onto the left point, right? Pulled it back along the function, right? Okay, so this will match that. You'll like this better. So one more time. What's our delta y going to be then?
X minus F of X.
Good, okay, so we're going to get f of x minus f of c. That's our delta y, isn't it? Okay, what's our delta x going to be? X minus c. Okay, make sense? Okay.
Why is that one different than the, like, why does just change it to C, make it not X plus C, F, C, X plus C?
Well, because the way we drew this here, and really we could draw this either way and it would be fine. Because we're going to take a limit here in a second and it's going to make it irrelevant because the distance between the two is going to shrink to 0. But it's more convenient to write it this way because then when you're finding the difference in the values, you're taking the greater value minus the lesser value. So we get x minus c and f of x minus f of c, which is the way that the difference quotient is traditionally written. Okay, they had it kind of mixed up in the book. It doesn't really make a big difference. So then if we're going to define a derivative here, what's our derivative gonna look like this time? So we've got, now another way we can say this is f prime, but we're gonna go ahead and say f prime of c, because we're gonna let c be kind of our anchor point, and we're gonna, x is the variable, c is kind of the fixed point. C is like a constant, x is like a variable. We're gonna change the value of x so that we pull it back onto c, right?
So make it 0, right?
Right. So we're gonna calculate f prime of c, and when we're all done, we're gonna get some answer in terms of c's. Let's just say hypothetically for a second. I want you to kind of look ahead and just see this. What if we got the answer f prime of c equals 2c plus 3? Then what would be f prime of a?
2a plus 3.
Or f prime of x, which we might favor because typically x is our independent variable. What would we get?
2x plus 3.
Right? So it's real easy for us, even though our answer is written in terms of c's when we use this formula technically. It's real easy for us to say, oh, okay, well, so what's f prime of x? Just change the c's to x's. And then it's a generic general function, right? Okay? So f prime of c then is just going to be the limit of
fx.
delta y over delta x, right? That's all a difference quotient is, right? That's all that means is just changing y over changing x. So the quotient is going to look like this, right? There's delta y, f of x minus f of c over delta x, which you told me was x minus c. Now, what do I want to do with this limit? I'm going to take the limit as what approaches what to get this thing to look like, instead of a secant line, to make it look like a tangent line.
X minus c approaches x.
As, how about as x approaches c, okay? Does that make sense? Because x is the variable, so x, it makes more sense in a way to let x be the thing that we're going to change, right? Okay, that is a perfectly analogous form of the difference quotient and therefore the derivative of the function. They both work identically. You can see they do the same thing on the picture. It's just that sometimes this is a more convenient way to write the algebra, okay? Let's look at just a couple examples where this might be, I mean, just so we get a little experience using this one. It's not like you're going to do a whole heck of a lot with either one of these, honestly, but just so you see this one in action, so to speak. So let's try about this. What if we try? We'll use this to sort of reinforce and review the idea about continuity and differentiation. So let's take, for example, the greatest integer function. Let's say f of x equals the greatest integer function of x, right? And so if we drew a quick graph, that's our stair step, right? So it's going like, et cetera, et cetera. Right?
Mm-hmm.
Okay, so let's take, for example, let's take the derivative of this as x approaches 0, how about? So let's calculate f prime of 0. Okay? So what do we get there then? We're going to get f prime of 0 equals the limit. And let's write down real quick so you can stare at it. Let's write down our new alternate form of the derivative definition too. So f prime of x, or c, equals limit of over as x approaches c?
Yeah.
Okay. All right, so what do we get then? So we're going to get f prime of 0 for our function is going to be the limit of the greatest integer function of x minus the greatest integer function of 0, right? Over x minus 0 as x approaches 0, right? Okay, but we have a problem here, don't we? We're gonna need to maybe do this as two one-sided limits, right? Because look what's happening. Here's 0, right? As an ant approaches from one side, he's gonna see something different than he does from the other side, right? So let's go ahead and let's make this one arbitrarily. Let's make this one the limit from the right. So we're approaching from this side, okay? So what's this gonna become then? What is, if I make this, then if I try to evaluate this, I'm gonna get a greatest integer of 0 plus there. What is that? What does the greatest integer function give me back at 0.000001? Gives me back exactly 0, doesn't it? Right? So this is gonna give me then, on the top, I'm gonna get 0 minus, what's the greatest integer function of 0? 0. What do I get on the bottom?
0.
Oh, it doesn't seem like it helped very much, does it? Okay, but the bottom is not really 0 minus 0. Ah, it's 0 plus minus 0, isn't it? 0 plus minus 0 is what? 0 plus. Right? Okay, do you see the difference? The greatest integer function of 0 plus is what? 0. Not 0 plus. It's exactly 0, isn't it? Because of the shape of the function. Think of the definition of a greatest integer function. The greatest integer function spits back the greatest integer that is less than or equal to the input, right? So if I put in 0.5, I get back exactly 0. So I'm sliding the b to the left until I get to an integer, right? If I put in 0.000001, I still get exactly 0 back. So the top of this thing is truly 0. So my answer looks like 0 divided by 0 plus. What's 0 divided by 0 plus? Well, that's undefined. That's infinite, isn't it? I get 0 divided by some number, which is infinity. Okay, make sense? So the limit from the right gives me back an answer of infinity. How about from the left? F prime of 0, and we'll call this, well, we'll take our limit from the left. I'm going to get the limit of greatest integer of x minus greatest integer of 0 over x minus 0 as x approaches 0 from the left. Okay, now based on our picture, yep.
Isn't 0 divided by anything 0 except 0 divided by...
Oh, I'm sorry. Yeah, yep, I'm sorry. We got that backwards. Whoops, sorry. Sorry. Yep, thank you. What I was thinking. So this answer is 0, sorry, yeah, because we're getting 0, true 0 divided by a number. Yeah. So now I was flipping my thinking around. What do you think is going to happen for this one? No, okay.
No, it's different.
There we go, yeah, something different. Okay, so on this one,
It's -1.
I am recording this, yeah. So what happens on this one is, as x approaches 0 from the left, so we're over here somewhere now, right? What's the greatest integer of like negative 0.01? Negative 1, right?
It always goes to the solid close down.
Right, so remember, kind of the mental picture you draw for yourself, imagine an infinite piece of wire with knots at every integer, and you can slide, like the value of a number would just be where that bead is on that number line, right? You can just slide, what the greatest integer function always does, is just slides everything to the left until it gets stuck on a knot, right? It's kind of a good way to think of it. So if I'm at negative 0.000, I'm right down there, aren't I? Right, on the function. And so the value of the function is -1 exactly. So I get back -1 minus 0 divided by 0 minus 0 is just 0 minus, isn't it? Right? Does that make sense?
Wouldn't it be 0 plus?
Well, a number slightly less than 0 minus, does it change anything to actually subtract 0 from something?
No.
True 0? No. So I get that, don't I? Okay, so that ends up being -1 over 0 minus So what's that gonna be? If I have a 0 on the bottom,
Positive infinity.
okay, good, it's infinity, and negative over negative makes it positive, right?
Yes.
And so, which makes sense. If you think about this visually, look what's happening here. As we draw closer and closer and closer to 0 from the left, the 2 points that we're using to calculate a slope start to line up vertically, don't they? Right? The slope goes from being, you know, there's a slope, but now it starts to get vertical, right? Which that makes sense. And so we're going to get a positive infinity for our answer, because that's what this thing is tilting towards, infinity, from positive slopes to bigger positive slopes approaching infinity, right? As the point slides to the right, as this ant walks to the right. Okay, on the other side, well, we just always have, as he walks along there, those are all horizontal tangent lines, right? Because as he walks on that step, the slope of the line on that step is 0, right? The slope of that segment.
So it doesn't matter if there's an open hole or not?
It doesn't make any difference, because in the limit, he never gets there, right? He just gets arbitrarily close. So why did I bring this up? We've already talked about this a little bit, but I wanted to take this opportunity to use this new alternate form to sort of demonstrate where we actually calculate what these slopes are. It was a little bit easier. We don't have those delta x's in there. In this case, it made things a little bit easier, right? One other one that it helps on.
We should always do something.
What's that?
Can we always do something?
You could, but actually a lot of times I think a lot of times it's better to use the other one. Just a few cases where this one is a little bit easier. We'll see it more when we do antiderivatives. With antiderivatives, then there's some things that you have to make some tweaks that it won't work the other way. There's really one technique that works and one technique that's super hard. But with these, they're almost interchangeable. Yeah, Brian, you had a question?
So since we had to like use the 2 different limits, which one do we use for the tangent line?
So the answer is then, if they don't agree, does the limit exist?
No.
No, and so that's why we said that, review from last week, that the function is not differentiable at every integer value because there's a break in the function, right? And so what we find is whenever there's a break in the function thing, those are places where the function is not differentiable. Can't take a derivative.
So there's no change.
So, right, so there's no tangent line. Couldn't do it, right.
So, when we had this question on Math.4, we wouldn't have this question.
Well, you might have it, but there's really, it's almost a sort of, it's an abstract, almost a philosophical question. We now know a rule, right? We have, what are the 3 places where derivatives do not exist? Breaks,
Curve,
sharp corners,
Vertical tangent line.
vertical tangent lines. Yeah, so we know those 3 things. Whenever we identify one of those 3 things, we know that the derivative doesn't exist.
So it's no limit or no derivative?
So it's no derivative.
Okay.
Yeah, because there's no limit, but we're really more concerned about the derivative than the limit typically, okay? If we look at another quick example of this, we looked at this other, okay, we looked at this example the other day also, right? And there's just a couple things. I mean, we talked about this sort of conceptually, but I want to put some teeth into this a little bit. This is an absolute value function, right?
Yep.
Remember what we said about this? We looked at this and we said, okay, on the right side of this thing, the slope is +1. On the left side, the slope is -1, right? And so at the point, at the actual sharp corner there, we've got a problem. I think this is, to me, this is a pretty cool way of visualizing this. What we talked about, you might remember, was we said if there's any kind of a curve that's not sharp, if we focus in enough, we will remove all of the curvature, right? Make sense? Okay, but if it truly is a sharp corner, if it does change directions suddenly like this, you can zoom in infinitely and it will always look like a sharp corner. You're never going to flatten it out, right? And so we had a problem there because then this point right here, we can't define a slope for that point because the slope is defined by relating this point to the adjacent points, which don't really exist, right? That's a hokey concept, but the points next to that point are the ones that we use to create the tangent, right? What we want to do, remember, if I have a curvy curve over here, and at that point right there, I want to get a tangent line. Well, how do I get that tangent line? I get the tangent line by saying if I focus in really, really closely, the tangent line and the function will become parallel, locally speaking, right? If I focus in and focus in and focus in, right? And so in a way, and this is a kind of a big concept to grasp, but think about this. Do you see then that the tangent line, even though it only intersects the curve at one point, it's implicitly related to the points in the neighborhood of that point, right? The ones surrounding it, okay? So that's hence our problem. Here, no matter what we do, the neighboring points on the right are going to pull that tangent line to 1, and the neighboring points on the left are going to pull it to -1. They don't agree, and so therefore we can't have a tangent line, because the tangent line can't have a slope. Which one would you pick? Obviously you can't give preferential treatment to one side over the other. They're completely interchangeable, right? So sharp corners don't work. Okay, that's a philosophical way of looking at it. Let's look at it in a way that's more analytical. And this is good. This is a really, the book doesn't do this, but this is something that I think is very useful to know how to do. What we want to do here then is let's take this function and let's define it as a piecewise function, right? So we've done this before, you may not remember, but we've dealt with an absolute value function as a piecewise function. So that we'll call it f of x, let's just say. What's the describe for me the right-hand behavior as a piece of the piecewise function. What's it look like? F of x equals, what's the equation of that line? X, right? Y equals x. Right, because we're looking for the y value. Isn't this just the line y equals x? Right? So f of x equals x whenever what's true? What part, for what domain? When x is greater than 0. The function equals, what's the equation of this line? Negative x when x is less than 0, right? Okay. The value of the function is 0 when x equals 0. Okay, so there's our piecewise function. Now what we can do here is we can just differentiate this piece by piece, right? So if we differentiate all parts of this, we get f prime of x equals, well, the derivative of x, the right side, we know is 1. We'll have a trick to show that very soon. So when x is greater than 0, the slope is 1. When x is less than 0, the slope was -1. But what's the derivative here? Well, it doesn't make sense, does it? It doesn't make sense because you can't take a derivative of just a single point, right? And so what we end up getting is it's undefined at x equals 0, and that's why our derivative function doesn't exist there. That's just another way of showing it.
So when
Yep.
you did the piecewise function, we kind of like took the corner out.
Yeah, well, we looked at it in terms of taking derivatives of each individual piece of that more analytically. But we're stuck here because how can you take the derivative of a single point? You can't do it, right? There's no way to do this because it relies on a limit, and this piece by itself doesn't allow a two-sided limit. It's just a point, right? It's a single x value. It's not anything earth-shattering. I just wanted you to kind of see this from a slightly different perspective. Instead of just looking at a graph and talking about it sort of conceptually, there's a way you can show it analytically, right? Okay, so once again, undefined derivative. Is this a special case? No, it's just a case. It could be any function that has a sharp corner. You're going to get that same problem. Okay? Let's move on. Let's take some questions here. So you guys had this one. We're looking at this one. So find the lines that are tangent and normal to the curve, y equals 3 times the square root of x at x equals 1. So let's start off with, I don't care which version we take. Probably it might be a little easier in this case to maybe use the new form of the difference quotient, but it shouldn't really matter. You wouldn't. Just by doing some math, you'd eventually kind of see that. But it'll work either way. It'll work either way. So we'll call this f of x. So f prime of x then is the limit of f of x, let's make that a c, f of x minus f of c over x minus c as x approaches c. Let's get specific. What's our value of c? 1. Good. So c equals 1. Our function is 3 radical x, right? So then this looks like f prime of 1 equals the limit of, what's f of x?
3 square root of
3 square root of x minus f of c,
1.
3 square root of 1, right? Because remember, c is 1
And F is X minus.
over x minus 1. Okay, so then what do we get? We get as x approaches 1 is our limit, right? So we get the limit of 3 times the square root of x minus 3 over x minus 1. So we could, what do we do here?
Times both top and bottom.
Okay, we could do a conjugate thing, couldn't we? So this is, we looked at a bunch of stuff like this before we knew anything about derivatives. You guys did some problems like this, right, when we did limits. What about these 3's? What can we do with these 3's that might be useful? Good, pull them out. We'll factor them out. Very good. So we'll write this as the limit of 3 times the square root of x minus 1 over x minus 1 as x approaches 1. And now we'll pull that rationalizing technique, right, that you're talking about. Multiply by the conjugate. So we multiply top and bottom by square root of x plus 1. And this ought to look pretty familiar, right? What do we get on the top then?
X minus 1.
Good, we get 3 times, and then the product of that difference, of that conjugate product, a minus b times a plus b, just gives us a squared minus b squared, right? Over, get the cancellation. Now if x goes to 1, we just get 3 over square root of 3 over 2, right?
That's your answer?
Yeah. Okay.
Perfect, right?
Yeah, how about